This program was brought to you by Coller Institute of Venture at Tel Aviv University.
So my research group works mostly in modeling, and I will be talking about modeling and how modeling can help in monitoring processes of every aspect of water-related issues. So the main activities in our group are numerical modeling applied to environmental problems. Our main fund, most of the money that we use for our research came from research projects, and also from services that we provide, and which about 10%, only 10% of our income come from these services. And we are a multidisciplinary team. We have people from pretty much all branches of engineering and sciences. So our research areas, they focus mostly on coastal environments, but we also start working in recent years in inland waters. So we have a team of people working with hydrodynamics, ecology, water quality processes, and also in water resources. And over these past 20 years, we have been joined consortiums of 20 plus European research projects, and providing our expertise in numerical modeling. So why computational models? These are the premises of my presentation. Models today are among the most relevant scientific and technological advances that we have, and among many other things that we can take out from models is the fact that they can forecast conditions. And we were talking about water. This is sometimes an important issue. As we have seen, we can use all kinds of instrumentation to have real-time data, but that's how far it goes. We know things as they are right now, and with models we can go a step further on that. So models, and I will try to show these in a real quick way, have countless applications in the water sector. So we have seen here that we have plenty of methods to assess the state of the things as they are right now with all these equipment. So and we have data, we collect data. So the thing is, when we have data, we have sometimes this kind of data, we have values, and we interpret these values. And usually we use an educated guess, and we try to connect these dots, and we have something that we use to describe our systems. But the thing is that data sometimes is scarce because it's difficult to go to the field and collect data. It's costly, so we take the minimum necessary for that. But the thing is, sometimes data doesn't give us the full view of things. We have scarce data, we interpret it, but sometimes we fail on this. So data sometimes has a problem with temporal resolution. In the same manner, sometimes we have all these field campaigns to collect data, and this is an example from the Tagus estuary here in Lisbon, and we have these stations to collect data, and we go there and collect all this data, and then we make these plots and to interpret the state of things. But the problem is that sometimes we have these artifacts, and we don't know if they are real or not, so we get this incomplete view, sometimes erroneous view of the reality. So we also have a problem with the special representativeness with data. So with models, we can try to go around these limitations, and we can have outputs like these. We have continuous temporal outputs, and you can see a time series on the bottom, and we also have this special resolved image of the system. So we can fill in the gaps that we usually have with data, with field data. So the thing is, another good thing about models is that they are dynamic, and they can provide us temporal evolution of any given property, and it can also integrate the properties. We can see here a model result for water quality on the left side, and on the right side you can see at the same time the water quality and the water movement, so we can relate things. Models can relate all these different variables, physical and chemical and biological variables. So also, obviously when we are dealing with models, we need also data. So it's a complement between models and data. We need data to force our models, to initialize our models, and also we need data to validate our models. So a model is a really good tool once it is validated. So we always need data, but we don't need all the data, because the fact is, once we validate our models for any system, then we can use it with some degree of confidence. And finally, models have an advantage that no other method has, because with measurements, with all these sensors that we can use, we go as far as this moment. So now is as far as our knowledge on any given system goes. So with models, we can go a step ahead on this, because we can predict, we can forecast. So with models, we can reproduce the dynamics of the system in the past in an in-cast mode, what is happening right now in a now-cast mode, and also in a forecast mode. So this is an example for one of our products here. We know what is going, we predict, we can forecast the conditions in the ocean in terms of temperature and velocity, the current field, for our coast over the next 3 days. So we know how things are right now, and we can use satellite data to compare with our model, but then we can predict pretty much in the same way as the weather forecast. So why do we work with models? We started working with models back in '85 because we were dealing with environmental issues, and we had this problem with data. Data was not sufficient to describe the state of the system. So we start working on a model, first for the water, for a coastal system, and then over the years we have extended this modeling tool also to inland waters, to groundwater, and now we have an integrated system that can pretty much simulate all the water cycle inland, in the coastal areas, in the open ocean. We have a product which is our model that we develop here. It's called the MOID model, and it's an open source model, so everyone anywhere in the world can use it, and right now we have plenty of users worldwide. So the thing is, the model, in broad terms, it describes the movement of water and also the movement of everything that we can parameterize and is on water. Constituents, it can be biological properties, it can be chemicals, it can be any other thing that pollutants, any other thing that we want, both in coastal systems, open ocean, rivers, and also in the groundwater. So we can pretty much model some of the processes that have been addressed here before, like the filtration of water in the groundwater, in the aquifer, and we can model that. So our model, the MOID model, basically now is being used by a different range of fields in science, and is also being used by research and groups and development groups, by private companies, by port entities in the aquaculture industry, and as far as we know, we have more than a couple of hundred regular users, and we have also more than 2,000 registered users using right now, taking advantage of our model. So I will just provide some examples here, the things that we do, and some things that we have done using this model. I will focus more on the marine issues, but so right now, one of the things that we are providing over the internet is the forecast for the conditions in the ocean. We have different domains that we are studying. We have a domain for the Portuguese coast, also a domain for the Portuguese economic coast, and we provide these forecasts over the next 3 days on the conditions of the ocean for temperature, surface temperature, and also for the currents. So, and the thing is, to keep up with a system like this, we rely on data also from other sources, and this is one of the shortcomings of these models. We rely on data from other providers. In this particular case, we need meteorological data, also the ocean conditions and some predictions from other models, and also the tide to force our model. And afterwards, after we produce our estimates, we validate our model. We take the results that we get, and then we compare with the field data, or in this case, with remote sensing data. We compare with measurements made by remote sensing, and we compare with the sea surface temperature that we get, and we make all these statistics to know if the model is behaving correctly, so we can have confidence in the predictions. And also we compare it with field data taken from these buoys that are scattered around the world, and they just go up and down in the water, in the ocean, and take these measurements of salinity and temperature. And we compare these also with our model, because our model is a three-dimensional model. So we compare these measurements, these in situ measurements, with the predictions of our model for the same spot. So we can see if we are profiling correctly the water in the ocean. And so the thing is, with this kind, and I will use this example to illustrate the potential of models, we have, in this particular case, the Portuguese coast, and we can have for any part of this coast a full description, 3D description of the ocean. So, as I said before, we try to verify if we are reproducing correctly the conditions so we can have confidence in these results. And afterwards, after having these, we can look at specific parts or specific areas or local areas in the ocean and know exactly what the conditions are for any given properties. We can do this for the ocean, and we can also do this for inland waters, okay, for waters in watershed, in the aquifer, in the soil, and in reservoirs. So this is the range of applications of our model. So some examples. One Action Modelers is a company that is a spin-off from our group, and he works developing this model mostly for inland waters, and he also develops the interface that is tailored for according to customers' needs. And so this is an application of our model in an agriculture context to quantify, to determine the water quantity and quality to be used in agriculture, and also to assess and evaluate, and also hopefully forecast the water quality in the watershed and in the reservoir. So this is another example. This one is also from a spin-off from our group, and is an example that comes from Malaysia. They are trying to build this power highway in the Strait of Malacca, and this company was contacted to try to predict the pathway of oil dispersion in case of an accident, because this is a strait with intense boat traffic. So in the case that there is an accident, they want to know what measures to take, where to act. So they need to have these forecast capabilities to know where the oil is going to be transported. So they have linked all these information that they gather from different sources: meteorological information, ocean information, weather information, and then they perform these simulations to know if an accident occurs in any given area, what is going to happen to that particular oil that is going to be there. So they need to be proactive and take some measurements for trying to cope with these pollution accidents. So this is they have an interface on the internet, and users just go there and can specify the place where the accident is going to happen, or they predict it's going to happen, and then they can see what is going to happen afterwards. Also, the model is running in the backstage, so it's providing the results and the estimates over the internet. We have developed this particular technology because in 2002 we had this big accident with an oil tanker near our coast. So it was the Prestige accident, and we can see just to contextualize this problem, an oil tanker just went adrift, and it was carried out offshore. You can see the trajectory over there. It was taken offshore because they were expecting to have a major accident. So this was the tanker eventually broke down, and all the oil was spilled. And so we have this dispersion pattern of the oil that was spilled. This is on the bottom you can see a satellite image with oil dispersion, and on the top you can see the estimate of this the evaluation of this oil dispersion. And it started dispersing offshore and was transported near the coast. And we have lots of problems, pollution problems. At least Spain had some pollution problems in some of the beaches. And we tried to use our model back then to try to simulate this episode. And in fact, it already starts the animation, but you eventually will go to the start. So we just use our software to try to reproduce what had happened. And we were successful in doing this. So back then we understand that we need to have this capability in a forecast way, not to just go and reproduce something that have happened, but to try to know in advance what was going to happen. So we start developing the operational tool that we have today to try to forecast this kind of accidents. So you can see the oil being spilled in one spot and is being transported according to the ocean currents that are driven mostly by the wind here. So this prompted our investment in developing these forecast capabilities in our model. So today, as I have said before, we use our model in a range of applications. This one is, we have used in our model in this project, EU-funded project, to determine in the Portuguese coast where the optimal areas for energy harvesting are. Just to finish, another we have used in a completely different subject. We have used our model to try to predict impacted areas in the Portuguese coast for harvesting mussels. We have these red dyes, and they have toxins, and they can contaminate all the mussels. And we have used the model to make these based on known episodes of these red dyes, to know the transport of these red dyes and how they would affect over the next week other production areas. And we came out with sorry, I will just go there. We came out with this bulletin, weekly bulletin. It was in this project, Azimuth project, and together with other countries, we win this Copernicus Master Best Service Challenge for the European citizens with this particular forecast of the impacted areas with these biotoxins. And so this is a range of our applications. And just to finish, if you have interest in this, afterwards you will have downstairs this book. You can just take it and see it is a number of applications using our model, and you are invited to take one of the books and just have a look. Okay, thank you.
This program was brought to you by Coller Institute of Venture at Tel Aviv University.